Electricity and Electronics. This is Chapter 8, Combination Circuits, Series and Parallel. Lessons and review questions. Edited, explained and narrated by Hector Bello. Material from text shown. The objectives are to determine the equivalent circuit resistance for a given combination circuit, to determine the voltage drops in a combination circuit, to determine the current values in a combination circuit, to determine the wattage values in a combination circuit, and to apply combination circuit theory to troubleshoot a combination circuit. Some of the keywords discussed here are combination circuit, equivalent resistance, series parallel circuit. 8.1 Reducing a complex circuit. When solving a series parallel circuit, often called a combination circuit, you will use all of the formulas and techniques that you learned in Chapter 6 and 7. When one branch of a parallel circuit has resistors in series, you will use the series circuit formulas to turn those resistors into one equivalent resistor. When you come across parallel branches in series with other resistors, you will use your parallel circuit formulas to turn those resistors into an equivalent series resistor. The simplest way to understand this process is to work through some examples. 2 examples follow. Be sure to work through all of these steps. Reducing to a simple series circuit. Example 1. Look at the top of figure 8-1. Shown on your screen, there are 2 8-ohm resistors in parallel. In series with the 2 8-ohm resistors is a 5-ohm resistance. Again, in series with 2 8-ohm resistors is a 5-ohm resistance. To find total resistance for this circuit, we reduce the combination circuit to a simple series circuit. This is done by applying Kirchhoff's law of series and parallel circuits. Using the equal resistances method learned in Chapter 7, you know that 2 8-ohm resistors connected in parallel have a total resistance value equal to 4 ohms. This step is shown in the middle of figure 8-1. The combination circuit can be redrawn as a simple series circuit with a new resistor identified as R23. The new resistor, R23, is the equivalent value of R2 and R3 in parallel. The equivalent value of R2 and R3 in parallel is 4 ohms. Once the new resistor, R23, is drawn in series with the 5-ohm resistor, R1, you can see that what is left is a simple series circuit. The resistances in the new series circuit are then added, and the total resistance of 9 ohms is calculated. In the second example, the circuit is just a little more complicated. One more step must be taken when reducing the circuit. In example 2, there are 2 resistors in series in one of the parallel branches. Example 2, look at the top of figure 8-2. This combination circuit has 2 resistors in series together in one branch of the parallel circuit of the combination circuit. On the parallel portion of the combination circuit. Again, this combination circuit has 2 resistors in series in one branch of the parallel portion of the combination circuit. These series resistors must be added together before the parallel circuit can be reduced into an equivalent series resistance. R2 and R3 can be combined using the series circuit resistor formula to create an equivalent 12-ohm resistor known as R23, upper right in figure 8-2. Resistor 4, 12 ohms, is in parallel with resistor 23, which is 12 ohms. When the resistors are combined using the equal resistances method for parallel circuits, you create an equivalent resistance of 6 ohms. This equivalent resistance is noted as R234, bottom of figure 8-2. All that is left then is a simple series circuit with a total resistance value of 10 ohms. Reducing to a simple parallel circuit. A complex circuit can also be reduced to a simple parallel circuit. Look at the top of figure 8-3. The fastest method of solving this problem is to first combine resistor R1 and R2. This leaves you with a simple parallel circuit that can be solved easily using the product over the sum method or the equal resistances formula. Work through this example on your own. Some review questions for this section, 8.1. First one is to reduce the following circuit to its simplest form. So here we have a circuit that has both parallel and series features. And what we must do is to combine some of the resistors so we can get either a purely series circuit or a purely parallel circuit to simplify things. If at all possible, try to make it a series circuit. If not, make what you can into a series circuit, and what is left should be a lot simpler. First step is to write down your problem. Sometimes you can draw the circuit if it's not shown. In this case it is shown, but I drew it again on the right side of the screen just to clarify things a little bit. And I named the resistors so we can have a better idea during our computations of what resistor we're talking about. I labeled them. So we have 3 resistors, what appear to be in parallel to the voltage source, R1, R2, and R5. 2 resistors are in between the branches, R3 and R4. So we can see right away that we have 3 resistors that are already in series. So we can go ahead and find what that resistance is and combine it. More or less, you can look at it as combining those 3 resistors into one. That way we can simplify the circuit and make it a purely parallel circuit. So if we combine those 3 resistors that appear to be in series up on the top and on the right side, we could say that R5 equals to, since we're going to combine those 3 into the position where R5 is to make it simple, we can say that R5 equals to R3 plus R4 plus R5. This is the series circuit formula for resistance, total resistance. In this case, we have 10 ohm resistors for all 3 instances. So we add 10 plus 10 plus 10, which is 30 ohms. So we make R5 into 30 ohms. And we can just for now omit the other 2 resistors, which are now combined into R5, which is 30 ohms. So our resistance total, we can find out by using, since the circuit is now a purely parallel circuit, now we can use the formula for resistance for parallel circuit, which is our reciprocal formula. So we can say our total, or resistance total, equals to 1 over RT plus equals to 1 over R1 plus 1 over R2 plus 1 over R3. In this case being 1 over 10 plus 1 over 10 plus 1 over 30. When you add that, you get 7 over 30, or 7 divided 30, which is 7 divided 30 is 0.23. However, remember that we must get the reciprocal of that. And the reciprocal of that is 4.34 ohms. So in reality, we get 4.34 ohms of resistance. Step 2, or question number 2, is to reduce the following circuit into its simplest form. Again, we are encountered with a circuit that is not a series circuit nor a parallel circuit, but a combination of the two. But we look for features that we recognize as parallel or series. We recognize at the top of the circuit, if you look at the drawing made by hand, resistor 3 and resistor 4 up top, 40 ohms and 40 ohms. That is a parallel circuit. If you see resistor 5 and resistor 6, that is, those two are in series, as well as R1 and R2. Those are also in series. So there's a number of ways you can go about solving for this circuit, and we're just looking to simplify it as much as possible. So we can begin at the top with R3 and R4, which is a parallel circuit. But in this case, I decided to go another route by simplifying the other series resistances like R1 and R2. You can combine those as well as others, but I decided to go with that. R1 and R2 are 25 ohms each. You just add the resistances in a series circuit, that's 50 ohms. The other two resistances are R3 and R4, which again you can, in this case, you can, since there are different resistances, you can use the division of resistances. The resistance of R3 and R4, again, those are a parallel circuit, and we can basically divide, since those are both 40 ohms, they're the same. We can use the division method for that, where we just take one of the resistances divided by the number of resistors that we're talking about, in this case 2. So 40 divided 2 equals 20 ohms. That part of the resistor, the circuit is simplified to 20 ohms. Moving on to the next set of steps, we basically add the resistors R5 and R6, which equals to ultimately 10 plus 20 or 30 ohms. So that's simplified, and we have now a completely series we have a parallel circuit. Now we have a parallel circuit. However, we can still simplify some more. like R3 and R4 and R5 and R6 are still not simplified to the maximum, so we can simplify those. In this case, we have 20 ohms and 30 ohms. We add those, we get 50 ohms. So we end up with the circuit that's drawn on your lower left, on your lower right of your screen, number 2. That circuit is the simplified version. So we have 2 resistors of 50 ohms each in parallel, and we can use the division formula again, where R total equals to R over N, N meaning the number of resistors that are the same value. So 50 divided 2, we have 25 ohms of resistance for the circuit total. Total resistance in the circuit. 8.2, solving for voltage and current values. Finding unknown voltages and currents in individual resistors is a little more complicated in combination circuits than it was in simple series or parallel circuits. However, you have just learned the first step in finding those values. Reducing the circuit once the combination circuit has been reduced to a simple circuit. The source voltage can be applied and total circuit current can be determined using Ohm's law. If the total current is given, the source voltage can be calculated using Ohm's law. Once this information is calculated, the steps used to reduce the combination circuit can be reversed. This reversal allows you to determine the individual voltages and the currents through all resistor paths. Once again, the simplest way to learn this process is through examples. Work through the following 2 examples. Be sure to work through all the steps. Example 3, and we have those on the screen, figure 8-4 for you to follow, so please do. It shows the same circuit as figure 8-1, but a source voltage of 18 volts has been added to the circuit. Using Ohm's law, the total resistance value previously calculated at 9 ohms equals to ET equals to IT times RT, which in this case, voltage total is 18 equals to current total times 9 ohms. So IT in this case is 2 amps. The total current value of the circuit is 2 amperes. Once the total circuit current value is determined, it can be applied to the simple series circuit to determine the voltage drop values. Remember that the current anywhere in a series circuit is the same. Thus, 2 amperes of current flow through R1 and R23. The voltage drop across R1 is 10 volts, or 2 amps times 5 ohms. The voltage drop across R23 equals to 8 volts, or 2 amps times 4 ohms. See the upper right circuit of figure 8-4. Reversing the simplification process, R23 is restored to the 2 separate resistors, R2 and R3. The 8-volt drop is applied to each resistor, as is done in parallel circuit applications. Since the voltage drop in each resistor is known, Ohm's law can be applied to find the current values of each remaining resistor. Current 2 equals to voltage 2 divided current resistance 2, which is the same as current 2 equals to 8 volts divided 8 volts equals to 1 amp, or current 3 equals to voltage 3 divided resistance 3, which is equal to current 3 equals to 8 volts divided 8 which is also 1 amp. R2 and R3 both have current values of 1 ampere. In example 4, the second example, figure 8-5, as shown, is based on figure 8-2. The total resistance value of figure 8-2 was calculated in example 2 to be 10 ohms. The first step is to apply the source voltage of 24 volts to the circuit using Ohm's law. Voltage total equals to current total times resistance total. 24 equals to current total times 10 ohms, and current total equals to 2.4 amps. The total current is 2.4 amperes. The second step applies to the total current of 2.4 amps to the simple series circuit. By applying series circuit principles, voltage R1 equals to current total times resistance 1, and voltage drop at R2, 3, 4 equals to current total times the resistance at 2, 3, and 4. So voltage drop at R1 equals to 2.4 amps times 4 ohms, and voltage drop at 2, 3, 4 equals to 2.4 amps times 6 ohms. So voltage drop at R1 equals 9.6 volts, and the voltage drop at R234 equals 14.4 volts. The voltage drop across R1 has been found to be 9.6 volts. To solve for the voltage drops across R2 and R3 and R4, you must further reverse the reducing process. The resistor R234 is expanded into resistors R2, 3, and R4 in step 3. According to the parallel circuit theory, the voltage across R23 and R4 are both equal to E R234, or 14.4 volts. The currents through R23 and R4 can be found using Ohm's law once again. The current at R23 equals to voltage drop at R23 divided by R23. So the current at R23 equals to 14.4 volts divided 12 ohms. So the current at R23 equals to the current at R4, which equals to 1.2 amps. And the current at R4 equals to the voltage drop at R4 divided R4, or resistance 4, which is the current at R4 equals to 14.4 volts divided 12 ohms, again equal to 1.2 amps. The final step is to find the voltage drops across R2 and R3. Using the current of 1.2 amperes and Ohm's law, the voltage drop at R2 equals to the current at R2 and 3 times the resistance 2. The voltage drop at R2 equals to 1.2 amps in this case times 3 ohms, which equals to 3.6 volts. And the voltage drop at R3 equals to the current at R2.23 times the resistance of 3, or the resistor 3. So the voltage drop at R3 equals to 1.2 amps times 9 ohms, which equals to 10.8 volts. Not every voltage drop in current for each resistor is known. Practice is the only way to ensure understanding of the combination circuits. Always look for 2 or more resistors connected in series or parallel as a starting point for reducing the circuit to an equivalent resistance. Once the total circuit has been reduced to an equivalent series or parallel circuit, the voltage source can be applied and the total current can be found using Ohm's law. To change each of the equivalent resistances back to their original state, the process is reversed. As this is being accomplished, the principles of series and parallel circuits can be applied to determine the voltage drops and currents. With a little practice, you will master this simple process and gain an in-depth understanding of circuit characteristics. This will assist you in dealing with complicated circuits. Power in combination circuit. Power in a combination circuit can be calculated by using either the formula P equals I squared over I squared times R, or power equals the current squared times resistance, or the formula P equals voltage times current. These formulas can be used for each individual resistance or for the circuit as a whole. Total power in a combination circuit is equal to the sum of the individual wattages, regardless of whether they are connected in series or in parallel. Figure 8-6 illustrates how power is determined in a combination circuit. Review questions for section 8.2. 1. Calculate the total current in the following circuit. So what we want to find is the total current. For that, we simplify the circuit from what you see on the middle of your screen. On the top, on the right, on the left, you have your circuit redrawn for clarity, and on the right you have the same circuit simplified. So how do we get there? Step A, simplify the circuit. We find the resistance at 1 total. So we find the resistance R1 total. I'm going to name that for the resistance at the top of the complex circuit. So that equals to R1 divided 2, because we have 2 resistors that are the same value. So we can use that division formula. So that in that case, 10 over 2, or 10 ohms over 2 divided 2, which gives us 5 ohms. We find R total 2, or R2 total, which again is R2 divided 2, since we have again equal value resistors. This again is to simplify to make this a series circuit instead of a complex circuit or combination circuit. So R2 total is 20 ohms divided 2, which is 10 ohms. And the third resistor, R3 total, we have 2 resistors of unequal value, so we can use the product over the sum formula or equation, which in this case is 30 times 20 divided by 30 plus 20, which is 600 over 50, which in this case is 12 ohms. So we have found out or simplified our resistors. Now we solve for this series circuit resistance, since that is the problem or the goal. So we have resistance total equals to R1 plus R2 plus R3, in this case being 5 plus 10 plus 12 ohms, which is 27 ohms. So your resistance total is 27 ohms. Question number 2, what is the value of the voltage source in the following circuit? So we're given a circuit without a voltage source, and we want to find out what that is. It's a 2-branch circuit with 2 resistors on each of the branches of a parallel circuit. So we want to simplify each branch first. So we have the resistance at branch 1 and the resistance at branch 2, we want to know what those are. So to simplify, resistance at branch 1, if you want to follow number 2 on your right side of the screen, equals to the resistance at branch 1. That's the resistor number 1 at branch 1 plus the resistor at branch 1, 2. In this case, we have 20 ohms plus 30 ohms. That's again at branch 1, which is 50 ohms. Just a simple addition, since we're dealing with resistors in series. We do the same thing for branch 2. The resistor at branch 2, 1 plus resistor at branch 2, 2 equals to 40 ohms plus 60 ohms, or 100 ohms total. So we have our resistances at each branch of 50 ohms and 100 ohms. Remember, those are both now in parallel, so we have a purely parallel circuit, and we can go ahead and find out our voltage drop at, since we now have the voltage drop at branch 2, and we also have shown on the problem the branch amperage, or the branch current. That's all we need to find the branch voltage drop, which in this case, being a parallel circuit, we know that our voltage drop at branch 1 equals to our source voltage, so we go for that. So the voltage drop at branch 2, we know if we find out our voltage drop at branch 2, since that's where we have our amperage, that would be the same as our voltage source, since voltage is equal in all branches, is equal to the source in all branches of a parallel circuit. We know that by using the known laws, Kirchhoff's law. So E, or voltage drop at our branch 2, equals to current total times the resistance at branch 2. We know our current total for that branch, which is 2 amps, and we also have just found out our resistance at that branch 2, which is 2 amps times 100 ohms, and that gives us 200 volts. And since we know 200 volts at branch 2, that's the voltage drop at branch 2, we know that it must be the same for the voltage source, so we call that our voltage source and our answer. Troubleshooting a combination circuit. 8.3. Once the electrical concept of combination circuits have been mastered, troubleshooting such a circuit is a relatively easy task. In most cases, taking voltage readings of individual components is the most convenient method to use. Look for an open or short circuit condition as indicated by a voltmeter. Troubleshooting a combination circuit uses techniques developed for troubleshooting both series and parallel circuits. The methods used depend on what portion of the circuit is being tested. Look at figure 8-7. In part A, the voltmeter indicates an open circuit at series resistor R1, a voltage reading equal to the source. However, if R2 or R3 is open, you will not see a full voltage reading across them. See part B. If R2 or R3 is open, there will still be a complete path for current through the other parallel resistor. To determine if the resistors are open or shorted, the expected voltage drop value must be calculated and compared to the actual voltage drop reading. Look at figure 8-8. Current readings are excellent. Current readings are an excellent way to determine if the circuit components are operating correctly. But this method should be used only as a last resort if it involves desoldering the circuit to take readings on individual components. Total resistance can help determine if a circuit is operating correctly, but care must be taken to avoid a false reading caused by reading a component in parallel with another component. In part A of figure 8-9, the ohm meter is connected across R3. The resistance on the meter value should be equal to only R3. But notice that R2 is connected in parallel with R3. Hence, the resistance value on the meter will be equal to R2. To take an accurate reading with an ohm meter, one end of the component must be read. One end of the component to be read should be disconnected from the circuit. Part B. To prevent reading other components in the circuit, compare parts A and B of figure 8-9. A component connected in parallel with another component or device in a complex circuit design can be very difficult to detect on a printed circuit board. A false conclusion about the component being tested can be reached easily. A schematic of a complex combination circuit is essential in order to properly identify which components are connected in series or parallel with other components. Most electronic systems will have a schematic available. Good technicians use them as an integral part of the troubleshooting process. Some more questions. Review questions for 8.3. The current readings should be used as a last resort in troubleshooting a combination circuit if what needs to happen, and that is desoldering. Soldering could damage components and complicate troubleshooting a system. Number 2, what might cause a false reading when checking a resistance in a combination circuit? And the answer for that is reading components in parallel, as you may read the good component as in schematic 8-9, and that's provided on your screen on the lower right. The summary for the chapter: any complex combination circuit can be reduced to an equivalent resistance or simple circuit. After the total resistance of a combination circuit is reduced to a simple series or parallel circuit, the source voltage can be applied and the total current value determined. After total current is found in a combination circuit, the original circuit can be reconstructed and individual voltages and currents found by applying the characteristics of series and parallel circuits. Total power consumed by a combination circuit is equal to the sum of all individual component power consumption wattages. Troubleshooting a combination circuit uses the techniques developed for troubleshooting both series and parallel circuits. Some more questions. Test your knowledge for 8.8, chapter 8. A combination circuit can be reduced to a simple parallel or series circuit. 2 or more resistances in a combination circuit can be reduced to a series resistance. Question 3. Using the circuit that follows, solve for the unknown values. This type of circuit is familiar since we worked on one that's almost identical on a previous problem, but we'll follow this one along since there may be a few differences. Again, we are solving for the unknown values, which are on your lower left side of your screen. They have already been filled in, but we'll work the computations so you can see how we went about finding those. First, we find the resistance at R1. Meaning the combined simplified resistance at R1, not necessarily the resistor 1, which we know is 10 ohms. So the resistances at R1 of this circuit, we can see they are in parallel. How do we find the resistance of a parallel circuit that have two identical values? We use the division formula for that. R1 divided 2, which is 10 ohms divided 2, or 5 ohms. We simplify R2, the twin parallel resistors are R2. We find that again, since they're the same or they're of equal value, we can use the same formula, division of one of the resistances by the number of resistors, which in this case is 20 ohms divided 2, or 10 ohms. For the third resistor set at the bottom of the circuit, we have two resistors of different values. We can use the product over the sum formula, or in this case 20 times 30 divided by 20 plus 30, which is 600 divided by 50, or 12 ohms. Then we solve for the series resistance total. Since we have a circuit that has now, since we have simplified it, is a purely series circuit, so we add those resistances. In this case, 5 plus 10 plus 12 equals 27 ohms. So we next move on to finding the resistance total. We find the resistance total with equal current values. So we need to find our current to find our resistance total, our voltage, or our current total. We have to find our resistance total to find our current total. So for that, we use Ohm's law formula. Current total equals to voltage total divided resistance total. We know our voltage total is given to us 10 volts, so we divide that by our resistance total that we just found out is 27 ohms, and that gives us 0.37 amps, and that is our current total. So we take our current total to find our each resistor voltage drop. Since we know in a series circuit, current is equal at each resistor location. So we use that across all of our resistors, which are now simplified. So the voltage drop at R1 equals to the current total, or 0.37 times 5 ohms, which is 1.85 volts. At resistor 2, the voltage drop at resistor 2, we have 0.37 amps times 10 ohms, which is 3.7 volts. And the resistance drop at resistor 3 is 0.37 amps times 12 ohms, or 4.44 volts. In our next problem, we simplify the circuit again to find the values that are asked for in the problem. There's a variety of things or values that they want us to find out. Only a few are given. They give us no voltage total. They give us no current at each resistor. They only give us a branch current, branch 2 current, and they give us resistor values at each branch. So that's all we have to go by right now if you want to ignore everything that you see in the circuit and just go by what the text gives us for now, just so we can work each step of the problem out to find each of the values that are supposed to be blank in the text. So We start by simplifying our circuit branches, branch 1 and branch 2. We're going to call it RB1 for the resistance value at branch 1, which equals to resistance 1 plus resistance 2. Remember, that's at that branch, or at branch 1. So RB1 equals to 20 plus 30 in that case. Those values are given to us. And we're just adding a series resistance, series circuit resistance, 20 plus 30 in this case, which is 50 ohms. And we move on to branch 2, RB2 equals to R1 plus R2. RB2 equals to 40 plus 60 ohms in this case, or 80 ohms. We have our two branch resistances of 50 ohms and 80 ohms. Moving on to the next step, our resistance total. We now have a purely parallel circuit, and we can find our resistance total using our formula, which is the product over the sum formula for resistance. So RB1, which is our resistance at branch 1, times RB2, resistance at branch 2, divided by RB1 plus RB2. That is the formula we're going to use. So it's 50 times 100 divided by 50 plus 100, which is 5,000 divided 150, or 33.33 ohms. The next step is to find our voltage drop at each branch. Since we have simplified each branch to one resistance value at each branch, we can simply use the Ohm's law formula, which is simply voltage times current, voltage equals current times resistance. But in this case, we call it the voltage at branch 2 equals to the current at branch 2 times the resistance at branch 2, which in this case is 2 amps times 100 volts, or 200 volts. So the voltage drop at branch 2 equals to 200 volts. And we know that in a parallel circuit, voltage at each branch is the same as your source voltage. So your source voltage must be 200 volts. With that, we can find our current total, which is 200, or the voltage total divided by your resistance total, which we know both of those. We know our voltage total is 200 divided by our resistance total, which is 3.33. That gives us 6 amps. So now we have our current total. Since we have our current total, we can figure out one more thing, but we'll leave that for the next step. To figure out the power, just really quick, power total is nothing but the power formula of power, or P, equals E times I, or power equals voltage times current. In this case, voltage 200. Our current total is 6 amps, or 1200 watts. The next step is basically figuring out what our branch current is for branch 1, which is the one that's not given, and we simply subtract our current total minus branch 2 total, or branch 2 current, and that simply gives whatever's left must be our current at branch 1. So 6 amps, which is your current total, minus 2 amps, which is the given branch current at branch 2, is 4 amps. So our current at branch 1 must be 4 amps. So we will assume that. And we can go further and say, since in a series circuit, next step, the current is equal at each resistance location as shown, then we can go ahead and find each resistor value with that resistance. So we know in branch 1 each resistance at each resistor value must be 4 amps. At branch 2 each resistor location must have a current of 2 amps each. So we can find each resistance voltage drop at those locations. We begin with voltage drop at R1, which is the current at B1 times the resistance at 1. In this case is 4 amps times 20 ohms. Which is 80 volts. We do the same thing with the resistor, the voltage drop at resistor 2, which equals to the current at B1 times resistor 2 value, which is 4 amps times 30 ohms, or 120 volts. Same thing with the resistor, the voltage drop at resistor 3, which equals to the current at B2 times the value of R3, or 2 amps times 40 volts times 40 ohms, equals to 80 volts. And lastly, we do the same thing for the voltage drop at resistor 4, which equals to the current at B2 times the resistance value of 4. And we have 2 amps times 60 ohms, which is 120 volts. We continue with the power at R1. We find that out, which is the voltage drop at R1 times the current at B1, or 80 volts times 4 is 320 watts. Same thing to find the power at resistor 2, which equals to the voltage drop at resistor 2 times the current at B1, in this case 120 volts times 4 amps, or 480 watts. Same formula used for the power at resistor 3, which is equal to the voltage drop at resistor 3 times the current at B2, or 80 volts times 2 equals to 160 watts. Same thing for the power at resistor 4 is equal to the voltage drop at resistor 4 times the current at B2, or 120 volts times 2, or 240 watts. So the power total is nothing but the addition of each of the powers. In this case we have 4 power at each resistor. So we have 320 watts plus 480 watts plus 160 watts plus 240 watts, which equals to 1200 watts total. That's the power total. And that is the end of the chapter 8. Thank you very much.